Maths for Planet Earth is an initiative which aims to promote integrating climate change and sustainability into the school curriculum beyond the usual subjects of science or geography. Our speaker, Miriam Zachau Walker, is a PhD student of the University of Oxford, where her research focuses on flexibility in high renewable electricity systems.
Hello, everyone. Sorry about not being able to unmute on time. Good morning. I'm a PhD student. I'm a researcher at the University of Oxford, studying, as she said, flexibility in highly renewable energy systems. But today I'm going to talk about something related to that called it Maths for Planet Earth, because we think that math is really important if we're going to work toward more sustainable futures. And as you may have heard in the last presentation, we talk a lot about solar energy, about renewable energy, but how do we know how much we need? How do we know what's going to happen in the future? And math can't tell us those things, but we can use mathematical tools to help start to answer those questions and to better understand what's happening on our planet. So Maths for Planet Earth is an initiative in the Environmental Change Institute in the University of Oxford, which aims to integrate climate change into the school curriculum, and especially into the math curriculum, because usually we talk about climate change in geography, sometimes in terms of what's happening with the science, but we can actually think about lots of other places in the school curriculum which are relevant to climate change, whether that's history or math. So many of you are familiar and may have even participated in some of the school's climate strikes that happened over the past years. And one of the big issues is about school curriculum and not accurately reflecting the climate crisis, as you see in one headline. Why isn't it being taught properly? But we actually think that there are ways to incorporate climate change, sustainability, and environmental research into the rest of the curriculum, and that math, although it doesn't seem automatically or as obviously related, is a really important tool. So we think that we can use math for climate change or to help mitigate climate change in research, such as climate models or trying to figure out how much solar energy we might need. But we can also use it in fields like policy and in activism. And in fact, mathematical models where people study the research can be used to inform policy. So you might think about, well, what do we need to do? How many EV chargers do we need? How much solar panel? How much money do we need to invest in solar energy or wind energy? Where should we put it? Are you going to organize a big protest? Are you going to figure out how many people you need to attend, what space you need, how much it's going to cost? So math has a lot of benefits, and it's really important that people who are organizing and who are making policy can interpret the statistics that come out of the research and can use these math tools, not very complex math tools, but can understand what's happening to go forward. So I'm going to talk today specifically about two mathematical models, and modeling is a subset of math. It's maybe not what you learn in school, but the same, it's just equations like you learn in school. You learn algebra, you learn statistics, depending on what grade level you're in. You learn geometry, whatever else. And these types of rules, these math rules, can be fed into models, and they can help us understand what happens in the world. So a mathematical model just uses equations, and those equations capture the relationship between objects in a system. It's not going to be perfectly accurate, but it gets the most important points. And we use this to understand a complex problem or a system better. So our planet is a really complex system, and we cannot possibly understand all of the different elements of it. But through research, we can understand some of those relationships, and we can better figure out how those things are related and what we might be able to do to address climate change. Then, more importantly, we can test out different actions or solutions without needing to do those experiments in real life. It wouldn't make sense to try and conduct an experiment on the scale of a planet. It would be irresponsible, too expensive, lots of reasons not to do it. So we can test out what would happen if we install more solar energy. What would happen if we do this with batteries? What would happen if we suddenly stopped polluting our rivers? And we can see, based on those mathematical relationships, what might happen in the future. So today, I'm going to take us through two very simple models. As I said, they're not going to be accurate in terms of a prediction for the future, but they give us an idea of how we can use math to understand these complex problems that are related to climate change, and then how we can use a mathematical model to look at one possible solution. And that question is going to be, if we have more renewable energy, we talk a lot about battery storage, well, how much might we need? And how could we use the tools that we learn in a normal math classroom, just in terms of equations, and try to use those to figure out these types of answers. And then at the end, I'll show you some resources that we have in Maths for Planet Earth that you can use yourself, because as you're studying, whether you're in the UK doing GCSEs or A levels, or whether you're somewhere else in the world joining us, these math concepts are the same. And so we have some resources on our website which you can use, which show how you can do standard math practice problems, but applied to environmental science and climate change. So at first, we're going to look at a very, very simple climate model. Actually, the website at the bottom is there, and so you could go to this website afterwards and play with it yourself. But let's look at what's happening here, because it looks a little bit complex. But this very simple climate model is looking at the relationship between temperature and carbon dioxide emissions. And this is something that's spoken about a lot when we talk about climate change, that we need to reduce our carbon emissions and we need to stop emitting carbon dioxide. So on the red axis, the one closest to the numbers and those red square dots, you see the temperature. And there's some lines. So the bottom line, just under 14 degrees C, is the pre-industrial temperature. And the top red line is 2 degrees above that. So when people talk about keeping the world temperature to 2 degrees, and we need to stay under 2 degrees, what they mean is that the average world temperature needs to stay at just below 16 degrees C. And so you can see historically what it's been, and it's been increasing quite significantly. And then we can look at the black and the blue lines. So the black axis and those black circles, which you read by looking at those points on the black axis, that's the concentration of carbon dioxide in our atmosphere. And that is related to the temperature. So if there is more carbon dioxide in the atmosphere, then we get into the greenhouse effect, which traps heat, and that will increase the world temperature. So when the sunlight comes in and when heat comes in, when it bounces off the Earth's surface, it then gets trapped in our atmosphere and warms things up. Okay. And then finally, on the blue axis, and those blue triangles are the rate at which we emit carbon dioxide into the atmosphere. So it's not just how much is already there, but every year we're emitting more and more and more into the atmosphere. And so this blue axis and these blue triangles, this is what we're going to look at in our mathematical model today. And we're going to say, what happens if we don't emit as much? What happens if we emit the same amount, more or less, or not at all? And what would happen then to those black circles, the amount of CO2 in the atmosphere? And finally, what would happen to the temperature? Okay, so we're looking and we're modeling the rate of carbon dioxide emissions and the temperature. And so scientists can use historical data, this data I just showed, to say, what do we think those relationships are? We can make an equation that matches up those red dots and those blue dots. And then we can use those equations and extrapolate what might happen in the future if we continue to do things as is, or if we make changes. So I want you to think about to yourself, if these trends continued, if every year we emitted more and more carbon dioxide, where do you think that temperature would be in the future? When do you think we would hit that recommended temperature limit? What do you think it would be in 80 years at the end of the century? So you can think about that for a moment. And then we'll see what happens if we plug those numbers into this model. It's just one equation. And we'll see that if we follow the trend, that means those blue circles keep increasing. We have more and more carbon dioxide every single year that we're emitting. Then we very quickly in this century exceed the 2-degree limit and have significant climate change. And this is why people talk about a climate emergency and why we're all here, because we want to prevent this. And so one of the great things about mathematical models is we can say, well, what if we didn't do that? What if we didn't? And so we can look at, say, if we just said, today, this year, we're emitting, you can see on the blue triangle in 2020 is about 10 or 12 gigatons of carbon per year. If we just stayed at the current rate, we didn't increase like we've been in the past, but we didn't decrease either, what would happen? And you could see we would have a lower temperature in the future, but we would still exceed that 2-degree limit if we just kept everything the same way it is today. So we do need to decrease this amount. Just staying put and not emitting more than in the past is not enough. We actually have to decrease the amount of emissions every single year. So what if we did half? So if tomorrow, everywhere in the world emitted half the amount of carbon dioxide, then we can see that we would actually stay under this recommended temperature limit, according to this model. There are more complex things in the world, but there is, the world would continue to increase. Climate change would still happen. Eventually, we would still hit that temperature limit. This trend in the red dots is still increasing, just more slowly. So it might not happen in your lifetime or mine, but eventually it would happen and climate change would still be happening, just more slowly, okay? So I want you to think about what would happen if we emitted zero. So if these blue triangles became zero, if we just tomorrow stopped emitting carbon dioxide, what would happen to the black circles? What would happen to the amount of CO2 concentration in the air? And then what might happen to the temperature? So you can think about that. There are some options on the side, and just think for yourself. If we halve it, things keep increasing. They increase more slowly, but they keep increasing. But if we eliminate it completely, if tomorrow we stopped emitting any CO2 into the atmosphere, then eventually the concentration of carbon dioxide in the atmosphere would decrease because we stopped putting things in. And eventually that temperature, where we have already seen significant changes historically, would start to come down. Now, it is unrealistic that tomorrow we stop emitting carbon dioxide, but it's not necessarily unrealistic that we get to a net zero future, hopefully in the coming decades in our lifetime. And some countries, including this one in the UK where we are now, have committed to doing that, having a net zero future by 2050. And so we can think about, well, mathematical models are part of what informed the policy to make that policy, because they could see that if action is not taken, then we could suffer dire consequences, and that the climate change and the climate emergency would continue getting worse. And so I think one of the things that we try to do at the Environmental Change Institute with Math for Planet Earth is to see that it's really important to continue studying math and to be able to understand what climate scientists say and mean. Maybe you want to be a climate scientist yourself, and that's great. Maybe you don't. Maybe you want to be an activist. Maybe you want to be a policymaker. Maybe you want to have a completely different job, but take climate action in your private life. And so it's still important in all of those roles to understand what information is coming out. So what we're going to do next is, this is great. This model helps us understand what is happening in the world and what might happen if we take certain actions, but it doesn't help us sort of go forward. So slightly closer to my own personal work and related a bit more closely to what the previous talk was talking about, we're going to look at another simple model. Again, just using the same kinds of equations that you can use, that you learn in your secondary school math. So we're going to say, how much energy storage would we need in a more renewable system? One way that we can stop emitting or reduce our carbon emissions would be to use more solar energy, wind energy, and hydropower, as was said in the previous talk. And so we don't know exactly how much solar power there will be. We don't know exactly how much wind power there will be, but we can use a model for a simpler system to say, what if there were only solar and wind, and how much storage we need? And that can help us understand what types of research might need to happen, what types of investment might need to happen, and what role storage can play in our system. And now the question is, why do people talk about storage? Why is storage so important? Obviously, storage can't solve everything either, just like solar power can't solve everything, but together they have a lot of potential along with people's individual actions. And so if we look, this is a week of data from the UK. And on the top, we have demand. That's our use. That's how we use electricity. And so that's a week. You can see the first 5 days. You can see at night, starts at night, and then we have used more electricity during the day, and then it goes down again at night. And you'll see 5 days in a row. And then on the 6th day, we use slightly less electricity. That's because it's a Saturday, and we do actually use slightly less electricity during the day on weekends. I think there's a lot of reasons for that. But our lives as society, we have these patterns that include doing more and then using more electricity during the week. And then on the bottom, we have the same week, and the yellow shows the solar energy. So again, you have more solar energy during the day and obviously none at night when the sun does not shine. And then you have wind energy. So power from wind, and that does not follow a daily pattern, but there's some days with more wind, and then there's some nights with a lot of wind power, and some days with less wind power. And so the problem is that we need the power to be delivered when we use it. Okay, our electricity system is a finely balanced network where we need all the supply to match the demand. And when we use coal and gas, that's much simpler because we can just burn the coal and burn the gas when we demand the power. But with solar and wind, we can't control when the sun shines or when the wind blows. And so we need to store that energy so that we can use it when we need to demand, when we want to. Okay, so that's why storage is very important. So what I'm going to do is on the next slide, I'm just going to move those solar and wind. They're now on the top graph. And what I've done is I've added them together, the solar and wind. So the green graph shows us the total supply of power in our system. It shows us the wind plus the solar. So anytime the sun is shining or the wind is blowing, we have power available. And that black line is the same demand. That's when we want to use electricity. Okay. And so there are going to be times when there is plenty, there's even extra power available. And there's times when there is not. And so if you look at that graph, think about when there might be enough energy, when is there not enough energy? So when the green line and the black line are equal, that means that there's exactly the same amount. But if the green is above the black, what does that mean? If the green is below the black, what does that mean? So I've just put an A and a B. So in the A case, the green, so the supply is more than demand. So we have more than enough energy supplied at A. And at B, you see that the green line, so solar plus wind, is less than the black line. So they don't produce enough power. So what needs to happen is that extra energy that's produced at A needs to be stored so it can be released later and we can use it at B. So again, this graph from the bottom is just going right up to the top. It's the same one. And what we've done is we've just subtracted, we call it the net load. So there's one equation here. It's just subtracting the supply from the demand. Okay, so same deal at A. We have more supply than demand, or we have less demand than supply. So you'll see that at A, we've just subtracted the green line from the black line. And at B, the same thing. So at B, you can see that the red line is above the curve, which means at B, we still have demand that needs to be filled. So what we look at on this red line is when it's above zero, that means that we have unmet power demand. So there's electricity that people want to use that is unmet. And so we need to store the energy that is produced that's below the zero and release it when it's above the zero. So there's a little gray line I put in there now. So it looks almost the same, but we're just going to say, okay, the gray line can follow that. And so it needs to charge up in A and release in B. So when is storage charging? It's going to be charging when there's more energy, when there's more solar and more wind than electricity we demand. And it's going to be discharging at B. So it's going to be discharging when that net load or when the demand is more. So then the question is, okay, we know when it's charging, we know when it's discharging, but it still doesn't tell us how much storage we need. What size, how much do we need to actually install in our system? And in order to do this, we can use some math that you will have learned in A level if you're taking math, which I encourage you all to do. And that is called integration. So it's a bit of calculus. But even if you're in GCSE, the idea is that we're just going to add up all of the storage when it's charging, and then we're going to, subtract it when it discharges. So you can go through time at every moment in time, at every hour. We're either going to add or decrease the amount of energy in our storage. So that's how we get the curve on the bottom. So we had power on top. That's again the same curve, where at A we had more supply than demand. We had more solar, and at B we had more demand that we needed to meet. And so on the bottom, you can see that we're going to start with some amount of energy in our storage, and we need to discharge it to meet that little bit of unmet power before A. And then we can start charging. So where that red line and that gray line are below zero, we can add energy into our storage system. So that's going to be increasing because we're charging up all of that extra supply, all of the extra wind and solar power that we didn't need when the sun was shining and the wind was blowing. We can store all that energy and it can increase. And then at some point there's a peak, and that peak is when that red line above crosses zero. And then going into B, it starts decreasing. And that's because we need to discharge our storage to meet the unmet demand. So when there was more demand, when we were using more energy than the sun shining and wind was blowing, that extra energy needs to come from somewhere, and it can come from this storage that we have charged up. And so that can be decreasing. And then you'll see as things go on through time, then you might increase a little bit and decrease a little bit, depending on whether or not you're charging or discharging your storage. So you're always going to charge your storage when there's more wind and solar than you need, and you're always going to discharge your storage when there's not enough. Okay, so how much storage do we need? I want you to think about this graph. If you look, how much energy do you think would need to be stored at any time in the storage? So you can have a few minutes to think, or a few moments to think about that. Where, in terms of where would you look? How would you know how big your storage needs to be? And in this case, we would need the storage to be big enough to fill all of that. So for this 1 week, if the sun shone the way that I showed at the beginning, and if the wind blew that way, and if we used that much energy, then we would need a storage size that is equal to the maximum point here. So when the storage was as full as possible, then we could say that that's the smallest storage we can use. If we have anything smaller, we're not going to be able to meet all of our demand. If we have something bigger, well, it just won't fill up all the way, but it's usually more expensive to have something bigger than you need. So what's the minimum possible size that we would need? Okay, so this is how we would use math. So the math we used here was just addition and subtraction. We just took these lines, we added them, or we subtracted them from each other. And then we used some math that you learn in A level, which is integration. So that's part of calculus. And with these two mathematical concepts that you can learn in secondary school, we've been able to understand this simplified problem, and we've been able to take some data about how we currently use electricity, and we've taken some data from weather, so when the sun is shining or when the wind is blowing, and just based on those three types of data and two math concepts, we've been able to solve a problem of how much storage would we need to install. So that's great, because we need to have people who can make these decisions and who can figure out, what do we need to invest our resources in? How do we move forward? Now, many of you will point out that this was a very simplified system. We are not going to have a system which has only solar power and only wind power for a very long time, if ever, because there's also other renewable sources, even if we went to a fully renewable world. Okay, and that's okay, because one of the things we can do with models is just understand what might happen in the future. We can understand the relationships between these things, and we can see that if you have more solar power, you might need more storage, or if you have more wind power, you might need more storage, or actually maybe if you can mix them together, you might need less, because maybe this wind will blow when the sun isn't shining, and so you won't need as much storage because they can complement each other. And so models like this can allow us to investigate those relationships and to learn a little bit more about possible solutions to the future. And we could see what happens if we have more solar than wind than I did in this model. What if we increase the wind instead? Or what happens if we don't have storage? How much more solar power would we need? If we could only have 50% of the storage required, what else would the system need? So you can add in more variables. Once you have a simple model, you can make it more complex and add in more things. And it's the same math tools, you just have more complex equations. Okay? So the only other thing I want to point out about models is they really depend on the input. So one of the things with climate change is that it might change our weather patterns. And so this model assumes that the wind will blow or the sun will shine pretty much the same way it has been doing. And as we've seen with climate change, storms may get more severe, or so wind might blow faster or in different places. And if that becomes significant, then although the relationships that we found in this model are accurate, we might have to make conclusions which account for that uncertainty. And we might need to say, okay, well, this might be a little more uncertain. There's no right answer, okay? And one way to demonstrate that is what has been happening recently with the pandemic is, so we used to have this really nice weekly rhythm. And I pointed out that weekly rhythm when we looked at demand at the beginning. And so you'll see the weekends. So this is now a week, okay? And the red parts are weekends, and where I said we used slightly less power, and the gray parts are the weekdays. And you can see that from January, February, most of the past years, it's a pretty clear rhythm. And then when the lockdown rules were introduced in March here, first of all, we used just less energy in general. And it's because a lot of things were shut. And second, that weekday weekend distinction became less clear. Now, since then, things have gotten much closer back to normal. But it's important to remember that the models that we make are only as good as the inputs that we have and the information that we have. And this is something that if you see models in other fields, not just climate change, that's also true. So one of the things at the beginning with the pandemic, there are lots of models about what might happen with the disease. How does it spread? How many people will be infected or might be infected? And the models are only as good as the data we have. And because there was a lot of uncertainty at the very beginning, and even still there is uncertainty, their models are useful to understand what's the range of possible futures, but they're not going to predict exactly what's going to happen in the future. They're a tool we can use to understand what the range of possible things is, so we can prepare for the worst case and we can hope for the best case, and we can make the appropriate policies and we can take the appropriate actions, understanding that we don't know exactly what's going to happen, but we can use these tools to understand what might happen and what might be more likely to happen or less likely to happen. And if we change our own actions, how does that change the likelihood about what happens in the future? So if we change our own actions with carbon emissions, how does that change the likelihood that we're actually going to stay below 2 degrees within our lifetimes or within our grandchildren's lifetimes? If we are able to understand how much storage we will need, how much renewables we will need, then how does that affect what investments we need to make as a community or as a government in the future? So these are 2 examples about 2 different models where we can understand a system or we can test out a possible solution and use math to understand how that might work. We have lots of options. So if you have any questions, feel free to put them in. And while you're thinking about questions, I'll just show you some of the resources we have on Maths for Planet Earth. So we have a website, mathsforplanetearth.org. This is from the Environmental Change Institute, where I'm a researcher. I'm doing my PhD in Oxford. But this is a resource for students and teachers related to integrating climate change and environmental science into the school curriculum. They're all math questions. They're modeled based on GCSE and A-level questions. So if you are studying in England, that will align very nicely. But even if you're studying elsewhere in the UK or elsewhere in the world, many of these topics are standard secondary school topics. And so we have a number of problems, whether they are geometry problems, differentiation problems, statistics problems. As you can see, this is just one option. So you can search by math topic, or you can search by environmental topic. So if you know that you yourself, or maybe your friend or one of your students, is particularly interested in one of these topics, and wants to do some more math practice or needs to do some more math practice, then you can also search by environmental topic. And as you can see at the top, there's also a suggest the problem thing. So if you yourself will have a problem that you have solved, or if you have an idea for a math problem that relates to environmental science or sustainability or climate change, then we welcome those suggestions. And that can be a fully formed problem that you yourself have written, or it can be ideas for a problem where maybe you have the sort of general sense of the problem, but we would be able to then make or adapt a problem to have more accurate or up-to-date data. So we encourage you to check out this site and to use these problems just, for normal math practice, or particularly because you're interested in the planet. So that is our site. And finally, I just wanted to say that as we've said before, we hope for a world where climate change is fully integrated into the school curriculum. And the reason we want that, of course, is because we want students to be able to take positive action themselves and to succeed in climate-friendly careers and just in their life. So we think that education is a very powerful tool and has a really important role to play, and that climate change education is extremely important and needs to be not just one, tick box. It needs to be fully integrated into the school curriculum in a way that students are themselves empowered for the future. So we would encourage you, as I've said already, to check out the Maths for Planet Earth website, but also if you, beyond that, can want to write to your government officials and go forward. So that's fine. And then finally, along the same themes, then we can prioritize education about climate change, sustainability, and the environment beyond just math. We think that education about climate change is very important. So I see that there are a couple of questions. So if you take some time to write them in, I'll read through them and be able to take a look. Let's see. So the first question is, when you talk about storing energy, is that batteries or some other type of storage? So that's a great question. I didn't say on purpose. So in the model that I used, we just use storage generally because there are other ways to store energy. And so in the model that I used, we just had, you just have to store it. And I didn't specify if it was stored in a battery or somewhere else. So another way, and in fact, the most common way that we store energy right now in the UK, is by using excess solar power and wind power to pump water up into dams. And we just store that water. And so it has, for those of you taking physics, gravitational potential energy up in behind the dam. And so we use this energy to pump it up the dam, and it stays up here. And then when we need that energy later, so when there's more demand than supply, we can release it, and you can let it fall like hydropower, so through a turbine, and then it falls and it releases that gravitational potential energy and spins the turbine, and then we can get electricity that way. So that's called pumped hydropower storage, and that's the most common form. But batteries are increasingly common, and obviously we can't build big dams everywhere. So we anticipate that battery storage will play a big role going forward. And so these types of models, you can put in different efficiencies. So the efficiency of that hydropower would be different from the efficiency of a battery. So here we have a question. Most people already know about solar panels and renewable energy, but stay with other sources for the sake of ease. How do we change this? Well, that's a big question. And yeah, I think there's a lot of things that we can do, but it's hard to do some of these things on our own because, in our own houses, we plug things into the wall and we're just kind of stuck with whatever's in the energy mix. So I think that some of that will have to come from bigger, from government investment or from private sector investment into solar panels or into renewable energy or to wind turbines, because the more renewable energy we have in the general energy mix, then the cleaner that energy is. But the other thing we can do to change it is you can put on, you can write to government officials, not just about education, but to encourage them to phase out coal, to encourage them to phase out fossil fuels, because if there are regulations that make it harder for fossil fuel generators to generate, or make it easier to be a renewable energy farm or generator, then there will be more of them. So creating the regulations and the markets for those to exist is probably how it has to be done, sort of at a higher level. I think on an individual level, if you have the means, people can install solar panels on their roofs. A lot of people do, but that's probably not big enough scale, large enough scale to change the full electricity mix. What makes me most excited about this topic? I've taken a circuitous route as well. I mean, I think energy in general, for me, renewable energy is a exciting topic because I think that it addresses can address two of the biggest challenges in the world. Obviously, we've been talking a lot about climate change and sustainability, but I think poverty is another really big issue, and I think renewable energy has the power to, or has potential to address poverty and energy access issues as well. So I think renewable energy is very exciting in that sense. And in terms of math, I don't know, I've kind of always liked math. I studied engineering originally and then actually became a high school science teacher. And so I think that sharing education about math and making sure that everyone has the tools to be able to understand what's happening in the world, to properly interpret data, is really important beyond just climate change. This is true whether we're talking about pandemic data. This is true whether we're talking about election data. This is true whether we're talking about whatever. People need to be able to understand and educated about the different numbers or models or conclusions that are thrown at them. And so I think that ensuring that we have an educated youth population who is then empowered to make their own decisions and contribute and shape the future world is super important. How do we convince people math is fun? This is a tricky one. For some people, it is really fun sort of automatically, including for me. For some people, it's much harder. I think one of the things with Maths for Planet Earth we're trying to say is that even if maths isn't fun for you, it's still relevant and important. And maybe you're bored at school looking at, math examples that have to do with sports or budgets, and they're actually relevant topics to things you might care about, like the environment. But some people like to see the beauty in math. Some people see it as a very practical tool that isn't fun but is useful later on. But I have to say that I have met a lot of people who wish that they had done more math later on. And so sticking with math, whether or not it's fun for you, I think is super a super choice. It's the last question, you all. Thank you very much for the time and for sticking with me. Check out our website and enjoy the rest of the conference.